I'm Tanner Gooding. I'm a developer on the .NET Libraries team. I am the owner of the System Numerics namespace, the System Runtime namespace, the System Runtime Intrinsics namespace, system buffers, and a few other areas. So I get the pleasure of helping to design, implement, and expose numerics, math, and other related APIs to basically everyone in .NET. Today, we're going to be going over one of the main new features in .NET 7, which is generic math, as well as just covering the past, present, and future of numerics in .NET. So to start with, we're going to go over the past 20 years of numerics in .NET. When we started in about 2002, we had the base set of integer types. So we had the sign types, sbyte, which is an 8-bit integer, int16, int32, int64. We had the unsigned types, and then we had the native sign type, or the native sized types, int pointer and uint pointer. We also had two base floating point types, single and double, which are binary based, and then the decimal type as well. We only had system math. It basically only provided support for doubles. There were very few operations that actually had integral or even single precision floating point support. And we were Windows only. We also were x86 only, and most of the floating point support was on the by87 FPU. This was before computers started adding things like SIMD support, which allows you to do more operations faster. Fast forward to .NET 4 in 2010. In .NET 2, 3, and 3.5, we basically didn't do anything. We didn't expose any major new APIs. We didn't expose any new types. The biggest change for .NET was really generics. And with generics, we didn't have the capability of exposing support for doing mathematical algorithms using generic types. So you couldn't take a T and then add it with some other T. The otherwise biggest change was just adding 64-bit support. And in .NET 4, we added support for big integer and complex. So that is numbers that have an imaginary and real part. And these were added to the new namespace System Numerics. Fast forward again to 2014, we have a slightly faster cadence here, only 4 years rather than 8. We started adding SIMD support. The types we exposed were variable size. They were on older hardware, they would be 128 bits. And on newer hardware, it could be up to 256 bits in width. We also exposed some basic types that were common for graphical applications. These were based on the XNA library that Microsoft had published previously. And so these were the vector 2, 3, 4, the matrix types, plane, quaternion, etc. Then fast forward another 5 years. Fast forward another 4 years. And we started working on .NET Core. We finally shipped .NET Core 2.0. This is about 2 years after I started working as a full-time employee for Microsoft. I started taking an interest and focus on trying to improve some of the things that I thought were missing from the BCL. So one of the first things I did was I exposed MathF. This exposed all the APIs that were on math, but extended them to support single, which is the float keyword in C#. So it's a 32-bit precision floating point numbers. We couldn't expose them on math because it would have caused overload resolution problems. One simple example is if you were to call square root 5, then in .NET Framework, that would the 5 would implicitly convert to a double, and you'd return a double. However, if you then exposed square root float on math, then due to the C# overload resolution rules, it would now call the single precision variant. So you would end up with less precision in your result, and it would still implicitly convert back to double. That was undesirable, and so we exposed mathf. We also started looking at and exposing other types like span and read-only span in .NET Core 2.1, which allowed us to greatly simplify various algorithms and support more types of memory access. And I started to push for achieving updated IEEE compliance. IEEE 754 is a specification that defines how the binary floating point formats are meant to be defined in memory and the operations they're meant to support. Fast forward to .NET Core 3.0, we're starting to do and ship new updates to numerics and math every single release. So we extend the APIs we expose on the math class even more to support more of the IEEE required functions. We expose additional rounding modes so you can better achieve the correctness you need for your algorithm. And we also started looking at exposing more types of SIMD acceleration. So we start exposing hardware intrinsics. And rather than the variable sized vector of t, we now have fixed size vector types. So we've got vector 64, vector 128, and vector 256 of t. These types are that many bits in width, and so you can use them in scenarios where you couldn't use vector of t. For example, you could use them as the backing algorithm for a matrix 4x4, because you know a matrix 4x4 of float is going to be exactly 4 vector 128 of floats. We also expose the raw APIs that give you access to the underlying hardware instructions for the CPU. And so we exposed an entire list of around 1,500 new APIs that cover all the ISAs for SSE through FMA and AES through PopCount. We also exposed a new class called System Numerics Bit Operations, where we started exposing helper APIs for various bit twiddling algorithms that many different libraries had as utility functions. And even throughout the BCL, we had many different implementations of these functions, but not all of them were as efficient as they could be. Not all of them handled the same edge cases like they should, etc. And so now we have this centralized class that allows us to provide all these core APIs with deterministic behavior, hardware accelerated behavior, etc. In .NET 5, we extended support for a new floating point type, which is half, which is 16 bits. We didn't at the time expose any operator support, however. We only exposed it as an interchange type. We also extended int pointer and uint pointer with associated keywords, inint and inuint, so that they could have first-class language support. We exposed a new constant called tau, which is 2 times the value of pi. We added more interchange APIs so you could easily transition between the system numerics vector APIs like vector 4 and the intrinsics APIs like vector 128. And we started adding hardware intrinsic support for ARM64 as well. Then in .NET 6, we just continued this even more. We added inint and inuint support to the math APIs. That way you could do things like max and clamp with them. We started adding overloads to divrem, which computes both the quotient and remainder of a division operation. So it returns a tuple, which allows it to be more efficient. We started exposing some fast APIs like reciprocal estimate, which computes 1 over x, but it allows some amount of imprecision so that it can be computed even faster when that's acceptable for your use case. We exposed a API in random that allows you to get a 64-bit integer. We exposed isPow. We added inint and inuint support to vector of t, and we shipped a preview of the generic math feature. So now we're up to .NET 7, which shipped last week. So in .NET 6, we existed in a world where there was no way to define a contract for operators. You had to define a new overload for every t you wanted to support. So if you wanted to support int and long, you'd have to have 2 separate overloads. And the logic across those implementations was effectively the same, give or take a few differences. You basically did all the heavy lifting yourself. So a simple example is if you wanted to compute a sum of integers, you'd have to write a for loop like this. You'd say int sum equals 0, you'd loop over the array, adding each index to the computed sum, and then you'd return the result. Now, if you wanted to support long, you've got the exact same code. You're just changing out the type from int to long, and everything continues working. We had no contract for operators. And so the solution for that was introducing static abstracts and interfaces. These let you define contracts for static members, including operators. The language understands the recursive constraint so that the operator no longer is restricted to the type being required to be the implementing type. And it's now stable in .NET 7. So for example, we have iAddition operators. This takes in 3 generic parameters, the first of which is tself, and it is recursively constrained. And it exposes an operator plus, which is defined as static abstract. Now, I'm going to briefly touch on something that's probably going to come up as a question of, why didn't we define this as something like iaddable? Or why didn't we define this as more math-oriented concepts like monad or monoids or groups or rings or fields? And the simple answer is computer math isn't real math. In real math, you have effectively an infinite domain, and you have a lot of rules that apply. Like you've got things like distributivity with multiplication. You have associative operations. So A plus B plus C is the same, regardless of whether you do A plus B first or B plus C or even A plus C. However, in computers, we have a very finite domain. We've got a fixed set of memory. We have constraints around performance and how much time it takes to compute things. And we don't have all the time in the world to get results back because we need to, render 1 million pixels every 60 times a second just to display a 1920 by 1080 screen. On top of running all the programs in the background, playing back audio and everything else. It's just a lot that the computer has to do, and we only have a finite amount of time to do it. So computers have fixed width types. We have int32. Not everything is a big integer that can expand indefinitely. And with this comes certain considerations like, well, you now have overflow. What happens when you have max value plus 1? It wraps around back to min value. You start having to consider things like, with floating point, there's implicit rounding after each operation. And so A plus B plus C can have different results depending on if you do A plus B first or B plus C or A plus C first. They can all have subtly different implications for your program. And because of that, concepts like monoids or groups or rings or fields don't map well to computers because they have implications about support that don't actually apply. They are also much higher math concepts, which someone who's only completed, high school math and has only taken something up to like algebra 2 may not be more deeply familiar with. And so someone who is looking for, hey, I just want to add 2 numbers together, they're not going to think to go look for rings or groups or fields to get the semantics they want. They're going to look for, I just want something called I add blah, blah, blah. And so we went with an interface design that maps well to the practical needs of programmers, as well as using names that are easy for people to understand, locate, and find. Getting back to the topic of, where we were, we had to define new overloads. But in .NET 7, that's no longer true because generics and static abstracts are paving the way. We can now declare a single method constrained with a constrained T, and we provide many interfaces out of the box to make this simpler for you. As Fred covered, one of these core interfaces is inumber of T. And so we can take our previous algorithm, we can change out int for T, we could constrain that T to be an inumber of T, and then we just rewrite our algorithm, with the only real other changes being that rather than using the literal 0, we have to use T.0. But this one function now replaces both of the previous int and long functions you saw and works for any other t that's constrained in I number. And so that includes all the primitive types built into the BCL. So decimal, float, double, int, long, uint, byte, sbyte, etc. It also includes other types like big integer and any future user-defined types that actually go and implement those interfaces as well. The logic is basically the same. And so we want to avoid having to repeat it. We also want to be able to expand to more concepts. Like one of the considerations if you're summing a bunch of ints is you might end up overflowing. And that would be bad. You don't want to silently overflow. You want to catch that behavior. You want to account for it, and you want to fail. This is in fact what link's sum method does, and it will throw if the sum of all the values overflows outside of the representable range. And so, an example is you can expand your original t to t input and t result. And now you can have two different types here. So you can have your result be one type, such as long, and your input be another type, such as int. You could also do this with int and double, or double and float, etc. And there's this special API called create truncating. There's actually 3 APIs here because there's 3 types of creation logic you might want to consider. But the basic premise is that create truncating does what a standard explicit cast in .NET does. Or rather in C# does, which is if you're going from a larger type to a smaller type, it will only take the lowest n bits. And so, long.max value converted to int.max value would become -1 because the lowest 32 bits of long max value are all set. And the bitwise representation for int is of that equivalent value is -1. We also have create checked, which will throw on overflow, and create saturating, which clamps the value on overflow. So in particular, if you have a value greater than, so for example, you have long.max value, and you're converting to int, it will become int.max value. And so it has semantics that are more familiar to some people who want to kind of set boundaries for their inputs or computations. You can learn more about the generic math feature in general by looking at the original design doc, the preview feature talking about it in .NET 6, the new blog discussing it in .NET 7, and then we even have an entire learning doc on the .NET documentation website that goes more in depth into generic math and covers some of the details. And we're going to go a little bit more in depth into generic math here after the slides, where I've got a demo presented that shows a more real world use case. Now, continuing on this, we've gone and expanded in our numeric space a lot of the cross-platform, a lot of the hardware intrinsics as well. So we had a very similar premise, which is that in .NET 6, you had to define a implementation for each platform. So if you wanted to support x64, you had to write one implementation. If you wanted to support ARM64 as well, you'd have to write generally a nearly identical implementation, and but just changing it to the equivalent APIs that ARM exposes. And this means that you can't trivially support future platforms. For example, WebAssembly is an upcoming platform for various architectures, including .NET, and they're adding SIMD support. But if you want to have your algorithm work on WebAssembly targets, you're going to have to go write an entirely new code path that does basically the same thing. And it's just going to keep expanding the more platforms you want to support. So for example, here's an implementation for x86 for basically doing a vectorized summation. So this is still doing sum, like I've been showing already, but it's just doing it using SIMD intrinsics to make it more accelerated. Now, you could use vector T because it's cross-platform, and it's accelerated but not fixed size. But this also comes with some downsides, like there's certain operations that are hard to expose. Dealing with constants is incredibly difficult. You can convert to hardware intrinsics to fill in some of the gaps, but it takes much additional handling. But the main benefit is it automatically scales based on your hardware. Whereas the vector types, they get all the same features, but constants are trivial and well known. They're fixed size, so additional operations are trivially possible. The only downside is being that it doesn't automatically scale to your hardware. And much like with generic math, we basically have the same improvements. The logic gets simplified down to a single path. The software fallback is technically no longer needed. It's just recommended. That way some code can execute on platforms where no SIMD acceleration is available. And the same algorithm gets simplified down to this one code path, which is a little bit more readable and can actually use operators as well. So what we landed in .NET 7 was generic math, the X platform hardware intrinsics, or IEEE math functions. We landed the 128-bit integer types, loads of perf and codegen improvements, and then improvements to big integer as well. And coming up in the tentative future, but no guarantees that we're going to provide it, of course, is we're going to be looking at providing bfloat16, which is useful for machine learning scenarios, parsing of hexadecimal-based floating point strings. We're going to be looking at more cross-platform hardware intrinsics, potentially some tensor types. Like I mentioned, more SIMD platforms like WebAssembly. We're going to be looking at exposing some of the IEEE decimal types. So these are like the binary floating point types, float, double, and half. But rather than being base 2, they're base 10. So they're more like system decimal, except they are standardized interchange types with well-defined semantics, and that other languages are also providing and standardizing on, whereas system decimal is a .NET only type. We're looking at rewriting big integer. We're looking at providing more in-box span APIs with vectorization behind the scenes. We are already working on providing AVX 512 and Vector 512 support. We're looking at providing ARM SVE, which is the scalable vector extension support. We're looking at providing vector masking APIs and more. And of course, if you have any ideas of your own, you should feel free to share them. You can file new issues on .NET Runtime. And the only request is that if you file an API proposal, to please follow the template. Simple ideas are always fun and fine, but the libraries team only has so much time to be able to focus on doing design work ourselves, in addition to everything that we're already working and focusing on. So if you're able to flesh out the idea just a little bit more and follow that template, it makes our job simpler, and it makes it more likely that we'll be able to review and get it in. You can also look at the area owner's doc to see who owns what area and who you should talk to if you want to kind of flesh out an idea a little bit more ad hoc and determine if there's any existing considerations, thoughts, ideas, or directions that want to be moved in for that area. Now, before we get to the QA, I'm going to show a kind of practical example. So, one of the core considerations for the numeric interfaces was being able to be extensible to all kinds of user types, all kinds of user scenarios, and more. So, like Fred covered in his talk, iAddition operators has that plus operator. It also has this operator checked plus, which is a new language feature in C#11, and it means that in a checked context, that is when you use the checked keyword and the corresponding braces to wrap the expression, this version of the method will be called instead. Whereas in an unchecked context, so the default, unless you change your project setting, or if you explicitly are using the unchecked keyword and braces for your expression, this implementation will be called. This allows user-defined types to do something that they've never been able to do before, which is to provide customized overflow behavior. So previously, of course, if you did int max value +1 in a user-defined type, with a built-in type. So if you did int max value +1, it would, in a check context, it would throw. However, if you wanted to define your own type, like int128, and you wanted to do the same, you couldn't. You could only decide to throw always or throw never. But now, with this, we were able to define int128. We were able to expose both the regular plus operator and the checked plus operator. And we were able to ensure that it correctly throws in the latter, but not the former. We also had considerations around, well, what if you have something like date time, where adding a date time and a date time isn't really something you do, but adding a date time and a time span is. So we had to consider, well, you can't just have one generic parameter, you need 3, because you need to be able to express date time plus time span equals date time. So we went and thought about all these scenarios. We thought about all the considerations and implications for number types, for more general types, and all the scenarios you may want to support in your libraries. And we made sure that these interfaces would work for them. We also had to, be somewhat restricting with some of the higher level APIs. We had to strictly define what it means to be a number, what operations are expected. We even had to consider things that most users forget about. For example, you may have defined your own type, you may have defined the addition operator, but when was the last time you remembered to define increment? Did you even know you could overload increment? Many users end up forgetting these small details and these things that overall end up making your type feel more complete. And so we strictly require that anyone implementing numbers provide those operators. We expect that they be provided. We expect they fit a certain shape. We even expect that things like unary plus come in, because even though they are a no-op, users end up relying on them in many contexts, and they are very trivial to expose and add on your type to make it feel more complete, more like a built-in type to the BCL would feel and provide. That also means that we consider things like, what are some of the most common operations users do with numbers? We consider things like, well, one of the most common things to do with types is you want to be able to process user input and display user input. And so that means we require that all numbers be parsable and formatable in some form. And, we got plenty of feedback from users saying that this is too much work and too much effort for their type. And our response was, these are core operations for number types. They're things that the consumers of APIs expect to exist. They expect to be able to display their types in a debugger. They expect to be able to take user input and process it. That's some of the earliest things you learn to do in C# is something like, you write a console program, you say, what is your name? The user types in their name. What is your age? And you do int.parse. You learn that users can provide bad input. So the next thing you do is you learn int.tryparse. And then you want to display that number back. And so these core things mean that parsing is just a core part of numbers, and we want to provide it everywhere. We also consider things like, well, some numbers are exclusively signed, some numbers are signed or unsigned, and we want to provide both. But if you're just constraining to number and you accept either input, well, you may end up in scenarios like wanting to be able to use to get the absolute value, which is a no-op for unsigned types, but which does something for signed types. And so even though iNumber base can be a signed or unsigned type, we still expose absolute value because it's something that you need, even if it's a no-op in some in some scenarios. But what this leads up to is a practical use case for all these APIs is you're writing some kind of game or graphics engine or rendering scenario. And one of the most common considerations is, well, sometimes I want float because it's the fastest, and sometimes I want double because it's more precision. So as a practical example, we can create this fancy bitmap renderer class, which is bitmap renderer of t, and we constrain it to be a struct with no reference types and a floating point type. And so we are able to generically write this one algorithm or this one type that now supports any floating point type. And so if we come to our code, we can see we just have this bitmap renderer of t float. And I've got these few small if-defs up the top. So if I go and let me run this in release mode. If I run this app, soon as it's done building, we'll see we've got a software renderer, and this is probably going to show up a little bit glitchy just because it's not going to correctly capture all the FPS available. But it's going to do everything using single, and it's going to render at about 470 frames per second or so. But let's say that float's not fast enough. Well, I want to use double, and it's as simple as just changing my using statement to be double. I rerun it. I change to the same bunny. I zoom in. I give it a little bit of rotation. And I turn wireframe off. And it's not running quite as fast. It's running a little bit slower at about 384 frames per second. But it is using doubles behind the scene. And everything still works. I only had to write one algorithm. Everything's good. And if I wanted to support half, that's simple too. I can do the same thing. I can render everything. I can switch to the bunny. I can zoom in. I can add just a little bit of rotation. And it continues working. But noting, there is a little bit of differences here. And it's running way slower. And the reason for this is ultimately that half has less precision than the others. It can only represent integral values up to 6,500 or 65,504. Anything above that becomes infinity. And so even though half works, there's some considerations and tweaks that you might have to do to your algorithm to account for all input types. So it's not always as simple as just, write one algorithm and go. Sometimes you do have to consider edge cases from the concept of I'm allowing any input. But in general, everything's still working, just the coloring is wrong. And, that's kind of the generic math feature. That's where we were with numerics and .NET, where we are now, what we're looking at doing in the future, and even a practical use case for these. And we're going to be looking at providing more APIs so that you have to worry about less in the BCL, and to make these kind of things even simpler in the future. So we're going to open for Q&A. Wrong thing. We're going to open for the Q&A, and I will start reading and answering some questions. All right, so just one question in the Discord so far. No, actually, there's two. So Tio asked, for your upcoming talk, what are your thoughts to the F# team's criticism of static abstract members? They felt so uncomfortable with it that they warn by default when defining or implementing interfaces with static abstracts. So ultimately, F# and C# are both .NET languages, but they are also very different languages. And the considerations for them, the things they want to support, the patterns they want to promote are different. F# is ultimately and primarily functional first. And with that, they have considerations. They've exposed features like SRTPs and other functionality, which C# doesn't have, which means that static abstracts and interfaces may not be appropriate for usage in that language, even though they're supported. It's kind of like in C# how sometimes LINQ is the right thing to use, and other times it's not. It's just another tool in your toolbox, and you want to consider which one is right for your scenario. And in F#, static abstracts and interfaces are not necessarily the best tool to always default or use. There's also considerations of, well, people can do the wrong thing with the API. In practice, most people won't do the wrong thing. Most people will end up doing the right thing. They will follow a general pattern and things will end up functioning well. But people can go overboard with any feature, use it where it's not supposed to be used. They can use it more extensively than it should. They can go hard set on, I always have to do this, even if it's not the right thing. Because sometimes when all you have is a hammer, everything looks like a nail. And so it's ultimately a good thing for F# that they're making the considerations of what's right for their language. And it's equally fine that C# makes different decisions, because C# is a different language and it's better for some things, whereas F# is better for others. Let's see, we had a question from Thinker on, did you ever consider adding something like a Math G class, which would be an alternative to Math and Math F, but with the generic variant of all the methods? We considered that at one point. We've ultimately decided that because of what's available with the numeric interfaces, we never need that kind of concept. Ultimately, all the primitive types implement their interfaces. And so all of the APIs that used to be available on the math class are now available directly on the double class. You no longer have to do math.square root. You can just do double.square root 5. You can do float.square root 5. You can do half.square root 5. Likewise, for integer types, you no longer have to remember system numerics bit operations blah. You can go and just do int.leading zero count. You can do int.isPow2. And moving forward, we're going to try to continue extending these existing interfaces with new members as appropriate. And so if you really, really need to use these in a generic context, you have a few different options, but the easiest of which is just constrain your t to the right interface and do t dot leading zero count, t dot square root, t dot cosine, etc., and it will just function. Flashover asks, what's the consideration behind previewing BCL APIs such as generic math interfaces in .NET 6? The basic premise is that since generics shipped in .NET 2, the ask for the ability to write algorithms generically, including using operators, has been one of the most requested features. So much so that we've actually attempted to design and ship the generic math feature at least 3 other times in the past. The most recent attempt before the one in .NET 6 and 7 was in roughly 2010. And each time we ended up deciding the BCL, the runtime, the language, everything just wasn't in the right place to provide the feature correctly to users. With us having open sourced, with us having made .NET no longer in-box and only on Windows, but rather cross-platform, and with versions being side by side, with the ability, with Roslyn existing and the ability to rapidly iterate on language features and provide more value than ever before, we finally reached a point where we were able to achieve all the things required to make generic math great. But it's still a massive feature. It's touching the most primitive types in the BCL. People from all corners of programming have different opinions on what's the right way to do it. And so we wanted to have enough time to design the feature, to ship it, to get feedback from everyone, and to make tweaks to ensure that it was correct. Because once we ship a feature, it's kind of frozen in stone. We don't have the option of going and making massive breaking changes. We have to make sure that it functions right the first time, or that it is extensible from that first shipping point without breaking it. And some features just require 2 releases because of that. Let's see, some other questions. Yes, I can provide a link to the repo later. The question was from Renaud on YouTube. But if you're interested in just a verbal URL, it's github.com/tannergooding/demo app. Just all one word. Let's see. Renaud says, I wonder if using SIMD in the numerics makes sense with the complex struct. I'm extensively using them, and I am thinking of using SIMD, but I'm not sure if it will improve a lot of the perf. Advice. So complex is basically it is roughly it is somewhat like a SIMD type, but not quite. Rather than doing the same operation on every element, you sometimes have operations that do different things on the real part versus the imaginary part. You have generally a type that may not fill an entire vector. So the smallest vector type for most hardware is vector 128, so 128 bits. And if you've got two doubles, that exactly fills it. But if you only have two floats, you're only filling half of a vector. So while there are some places where SIMD acceleration might be beneficial and might help, there's also places where it will equally hurt if you're only trying to do it on scalar operations, and where you may want to consider a custom algorithm when operating on arrays of complex numbers instead. There's a question from Speaker in Discord for what's the design status under plans for the iVector and iSIMD vector generic math, or was that scrapped? So it is something I want to expose. We didn't have enough time in .NET 7 to complete that along with everything else we were doing. iSIMD vector and iVector will likely be different types because they're slightly different concepts. iSIMD vector will likely specifically be implemented by vector of t, vector 64, 128, 256, and 512 of t, but likely not by vector 2, 3, and 4. And the reason is that iSIMD vector is really explicitly about modeling that this is a vector type that is backed by single instruction, multiple data instructions. And so it is guaranteed to be hardware accelerated, or at least be queried for hardware acceleration. And all the implications that come with that. So you want to do hardware checks, you want to do ISA checks, you have a limited set of functionality or a set of functionality that works on a broad set of types. iVector of t is kind of different. It's something more like I want to reserve for a more general purpose vector type. So something that's not necessarily directly tied to SIMD, and which directly corresponds to the more machine learning oriented side of vectors, which are more like arrays of values of the same type, and which may be arbitrarily sized. That one's even more complex, and it's going to be something that we look into in more detail when we take a look at tensors. Brainiac asks, what new features in .NET in the future might or will generic math enable? I think you named machine learning as one example. Are there other ones? So generic math will, within the BCL, we've already started using it to simplify many of our own algorithms. For example, we've been able to remove several hundred lines of code from LINQ, specifically the max, min, and sum methods by normalizing to a common API on the back end. In the future, we may expose more public APIs that are directly taking these generic math interfaces that allow users to that will allow our APIs to support more types, including user-defined types. This is ultimately similar to how we have many APIs that are generic and are constrained to where T is I comparable. And so it supports any type that supports comparison operations. Generic math basically allows the same thing, but now with all kinds of additional operations. So min and max, clamping, addition, subtraction, multiplication. We can define a standard deviation algorithm that works with any number type, etc. It really just means that we can take any kind of API we were already going to expose and make it support more types out of the box, and therefore provide more value to the community. Are there any other questions? There's no one talking after me, so I probably have a few more minutes if we do have any. Sergio asks, is this the talk to get gooding at C#? If you'd like it to be. Flashover asks, does the generic math feature require recurring template? Does the generic math feature and recursive template require runtime support? Yes. The IL specification made the original IL specification didn't allow for having static abstract members. And static abstract in general is kind of a weird concept, because when you're talking about standard virtual dispatch, you generally have some kind of virtual dispatch table, which is a member of the instance and allows you to look up and resolve all of the relevant data so that you can dispatch to the correct function. In order to get static abstract working, we don't have a place to store all of that state. We can't carry it around per instance, so we can't track, for example, when a derived type is passed around as a base type. So like you create an instance of derived, but you pass it as a base. We don't have the ability to track that it was actually derived in the first place. So we had to do all kinds of fun tricks to the runtime and the language and put some restrictions in place on how and where it was used to make everything work correctly, to make all of the information resolvable, etc. So it does require runtime features, and it is .NET 7 Plus only. Yes, that is Snorlax behind me. I can definitely show him aimbot. And that is a Mega Charizard sitting on top of him. That was made by one of my partner's friends for a birthday several years ago. They handmade it, and it was a very good job. Let's see, there was another question on shift operators. So in particular, Thinker, yes, before .NET 7, shift operators only allowed int as the second operand. For generic math, particularly because there's concepts like big integer, which can technically contain more bits than are representable by an int, and you have contexts like, let's say you want to use the output of a trailing zero count to do shifting, etc. And so C# relaxed that restriction, and now you can use any you can use you can use the containing type as the second operand as well now, or int. And that allows you to now do, for example, in a generic context only, C# directly still doesn't allow it. You can do long left shifted by long, or more in particular, T left shifted by T. Renaud asks, do you have any idea if AVX 512 will be supported? Yes, we're currently working on that. The initial support has already been and is being checked into the runtime. There's no guarantee it will be in for .NET 8, of course, but we are working on it. I even have the PR up to expose the library side of vector 512 of T, and that's just awaiting resolving a test failure on the mono side before that gets merged in. Tibaclone asks, will we see a Roman number implementation for the warm-up of Advent of Code? If someone wants to implement it. I'm personally not going to. I'm about to take vacation for the rest of the year. at least off from Microsoft work, I'll still be doing personal projects, work on my TerraFX, open source work, etc. But if someone else wants to go and implement some kind of Roman number implementation, they should feel free to do so. And then Micronet asks, does decimal create truncating work given that my custom number type has an explicit conversion to decimal? Or does decimal have to define all the types it can be created from? So create truncating, create checked, and create saturating support any, they are themselves generic, and they support any input which is itself also an I number. The user ultimately has to provide some implementation within their create truncating that does the conversion, or my custom number type has to provide a conversion to decimal itself. Internally, there's two protected only methods that are effectively create from, or that are convert from and convert to. And so either decimal or my custom number type can provide the conversion between the two types. In this case, since decimal's in the BCL, my custom number needs to provide it, but it can provide it and it can still work. The create APIs are probably the most complex thing to handle when you're implementing your own number type, just because you have to consider all the various different types of conversions. You have to consider whether you're converting from a type or to a type. You have to consider which of the two types provides the API, or even what do you do if both types provide conversion APIs, etc. It's kind of like all the problems that C# has to consider with when they're exposing new types and conversion operators. You just have all kinds of considerations that you'll have to take into account and do. But the general design has made it kind of simple to for users to reason about in some contexts. Right. I don't see any other questions right now. So I'll give it about another 30 seconds or so. And if no one else has any others, then thank you all for tuning into the talk. I hope you all enjoyed it. I'm available on the Discord or Twitter, and now co-host in Mastodon as well. If anyone wants to talk or ask other questions, either directly or indirectly. And of course, I'm always available for issues on GitHub as well.